Let's now go to the differential form of the mass balance equation, the mass conservation equation. An equation that we can apply to every point of the flow field. For this purpose, we consider within a fluid a cubical fluid element or a cuboid fluid element or dimensions dx, dy and dz as shown. There is a velocity field with component Vx, Vy and Vz. The rate of accumulation of mass within this volume would be, the volume is fixed, volume is dx, dy into dz. So the mass contained within this is rho times dx, dy, dz. The only way this mass within the control volume can change is if the density changes. And if del rho by del T is the rate of change of density within this control volume, then the rate of accumulation would clearly be del rho by del T into delta x, delta y, delta z per unit time. And this rate of accumulation should be equal to the net influx. Let's calculate the net influx. Let us consider the phase with a normal in the minus x direction, which is the phase there. And what is the rate at which the mass is crossing this control surface in time delta t across this phase is the density rho Vx times the area, which is dz into dy and times delta t. Next, let us consider the opposite surface with the normal in plus x direction or distance delta x away. This is the velocity is such, if velocity is positive, then the mass is moving out of this surface. So this is an efflux. That's why we put a minus sign. And we use the Taylor's expansion to get this expression for the net efflux across this surface in times delta t. Similarly, we write for the surface with normal in the minus y direction, in the plus y direction, in the minus z direction, and in the plus z direction to get these 6 expressions for influx and outflux. The net influx is obtained by adding these 6 terms, so that the accumulation delta rho by del T into the volume times delta T is given by the remaining terms of the efflux, the negative sign for converting this into influx. And the volume delta x, delta y, delta z cancels, delta t cancels, and the resulting equation is delta rho by delta t plus delta by delta x or rho Vx plus del by del y of rho Vy plus del by del z of rho Vz. This is equal to 0. In vector form, we can write this as del rho by del t plus del dot rho V. This can be expanded into del dot rho times V plus rho del dot V. Or this rather dot would be here, del rho times V. But this term and this term, what are they? This reminds us of the total derivative formula, Euler acceleration formula that we derived in this last lecture. This is nothing but d rho by dt, the material rate of change of density. And this results in d rho by dt, the material rate of change density, plus rho times del dot v is equal to 0. This is the differential form of the mass balance equation. Clearly, if the fluid is incompressible, by d rho by dt, the material rate of change of density should be 0. And then we get a simple expression, del dot v is equal to 0, or del Vx by del x plus del Vy by del y plus del Vz by del z is equal to 0. Since quite a bit of fluid mechanics deals with incompressible flows, so this equation is the equation quite often used as the equation for mass balance in the differential analysis. This equation is also known as the continuity equation. This is applicable strictly for incompressible flows or where we can assume the flow to be nearly incompressible, quasi-incompressible flows. Let's give an example of how we can use this continuity equation. The tangential velocity component in two-dimensional incompressible flow is given by v theta is equal to k by r, with k as a constant. What could be the possible radial velocity component? Clearly, we are now dealing with cylindrical polar coordinates theta and r in 2 dimensions, incompressible flow. So we'll use the form of the equation del dot v in cylindrical polar coordinates, and in cylindrical polar coordinates del dot v is 1 by r del over del r of r Vr plus 1 over r del v theta by del theta. And since v theta is a function of r alone, not of theta, the second term is 0. That means RVR is independent of R. From this is 0. This means that RVR must be independent of R. It should not change with R. That is, RVR can be a function of theta and t only, not of R. This gives VR is equal to some constant f, or rather some function of theta and t divided by r. VR varies inversely as 1 over r. There could be dependence on theta and dependence on time. If we talk of steady flow, there will be no dependence on time, so there could be a dependence on theta. All kinds of solutions are possible for this. The simplest, of course, is when f theta by t is 0. If f theta by t is 0, then Vr is 0. There is no radial velocity. The fluid particles are going around in circular path with only v theta velocity, which also decreases as r increases. So the velocity near the origin is very large, and the velocity dies out as 1 over r as r increases. This is known as a free vortex in fluid mechanics. We will have occasion to use this free vortex extensively in later calculations. The flow behind an aircraft consists of two trailing free vortices. You can see in this picture the vortice is rotating, the flow is rotating, the velocity is very large at the center, is slowing out as r increases. Another solution is when f theta t instead of being 0 is a constant, let's say minus k, then Vr is minus k over r. So there is a r velocity which also decreases as r increases but is negative, is directed inwards toward the origin. A bathtub vortex, a vortex that you see in a bathtub, or when you pull out the plug in a sink and the water goes around in circles and is sucked in, is called a bathtub vortex. An example of bathtub vortex is a hurricane. Hurricane can be modeled as a bathtub vortex. The fluid is moving circularly and there is a component of velocity towards the center of the hurricane.